All right, let's dive into one of the most powerful ideas in all of math, the function. Seriously, this is the secret language that mathematics uses to make sense of our incredible, always changing world.
So let's start with a huge question. Think about it. Everything around us is constantly in motion. How on earth can we use something like math, which feels so static and fixed, to actually describe that constant flow of change? Well, here's a good way to think about it. Basic algebra? That gives you a snapshot in time. It can tell you, okay, right now, x equals 5. It's a single frozen moment. But calculus, which is built on top of functions, well, that shows you the whole movie. It tells you the entire story of how we got here and where we're going. So how do we actually get from that single photo to the full-length film? We use this brilliant little tool called the function. And at its heart, it's a surprisingly simple idea. It's just a rule for turning one thing into another, an input into an output. Okay, so here's the official textbook definition. A function is a rule that takes an input, and for that one input, it gives you back one, and this is the absolute key, only one unique output. This one little rule is what makes functions so incredibly reliable and powerful. But, definitions can be a little dry, so let's think about it a different way. A really great analogy is to picture a function as a simple machine. You just put something in one end, the machine does its thing, and something new and specific pops out the other side. And the process is always the same, kind of like a three-step dance. First, an input, which we usually just call x, goes into the machine. Then the machine applies its special rule. Let's say its job is to square whatever number you give it. And finally, a single unique output, y, comes out. Simple as that. Okay, let's put this machine to work with a real rule. We're going to use the function f of x equals x squared. And that fancy notation just means our function, which we're calling f, takes an input x, and its one job is to square it. First up, the input. Let's feed the number 3 into our little function machine. And now the machine kicks into gear. It takes that input, 3, and it follows its one rule. It calculates 3 squared. And pop, out comes our result. The unique output is 9. For this specific machine, if you put in a 3, you will always get a 9. No exceptions. It's totally consistent. And that predictability is everything. Okay, so let's zoom in on that golden rule I mentioned before, because this is the one idea that separates a true, proper function from any other old mathematical relationship. And there's actually a super easy way to spot one visually. It's called the vertical line test. If you can draw a single vertical line anywhere on a graph and it hits the line more than once, like it does here with the circle, it is not a function. Why? Because that means one input x is trying to give you 2 different outputs, and that breaks our golden rule. A real function, like the parabola you see on the right, will only ever cross a vertical line once, no matter where you draw it. Every machine has its limits, right? An operating manual that tells you what it can and can't handle. Well, for our function machine, that manual is defined by 2 key concepts, the domain and the range. The domain is pretty straightforward. It's just the complete set of all the numbers you're allowed to put into the function in the first place, without making the machine spark and break. For some functions, you can throw any number you want at them. But for others, like one that involves a square root, you can't put in a negative number, so its domain is a little more restricted. And the range is just the other side of that coin. It's the complete set of all the possible results that can come out of the machine. If you go through every single valid input in the domain, all the outputs you get together make up the range. Okay, and this is where it gets really, really cool. It turns out there isn't just one type of function, there's a whole zoo of them. And each one is perfectly adapted to describe a different kind of change we see out in the real world. And this is where their true power really shines. Each type of function is like a specialist. Polynomials, they perfectly capture that smooth, predictable arc of a thrown volleyball. Exponentials, they model that explosive, runaway pattern of something like population growth. And trigonometric functions are perfect for anything that repeats in a cycle, like the vibrations of a sound wave or even the rhythm of the seasons. All right, let's bring all this together for the big payoff. Let's see how functions lead us to the ultimate promise of calculus, being able to measure change, not over an hour or a second, but in one single, fleeting instant. Think about driving on a long road trip. Algebra is fantastic for figuring out your average speed for the whole journey. Total distance divided by total time. But it has no way of telling you your exact speed at that one specific moment you glance down at the speedometer. That's a question only calculus can answer. See, with algebra, the best we can do is find the average rate of change. It's like drawing a straight line, we call it a secant line, between where your trip started and where it ended. The slope of that line is your average speed. It's a decent overview, but it misses all the speeding up and slowing down you did in between. But watch what happens as we slide those 2 points closer and closer together on the curve. Our straight line approximation gets better and better, right? The slope of this much shorter line gives us a way more accurate picture of our speed during that smaller window of time. And here is the absolute genius of calculus. What happens when those 2 points get so close together that they basically merge into a single point? Well, our line transforms into what's called a tangent line, a line that just kisses the curve at that one exact spot. The slope of that line is the instantaneous rate of change. It's the speed on your speedometer. And it has a special name, the derivative. And that's really the heart of it all. Functions aren't just some abstract rules in a textbook. They are the living, breathing language that math uses to tell the story of a universe that is constantly, beautifully in motion. So that leaves us with one last thought to chew on. If functions really are the language of change, what story in your own world, maybe in your job or your finances or even your fitness, could you now start to describe? Thanks for digging into this with me.